Hi physics friends, today we're going to be presenting projectile motion using vernier physics technology. This presentation is by Wendy Job, John Yantz, and Weston Leftwich. Our lesson objectives for this video are to use video analysis techniques to obtain position, velocity, and time data for a projectile, analyze the position versus time graph and the velocity versus time graph for both the horizontal and vertical components of the projectile's motion. Relate the horizontal and vertical components of the projectile's motion to any forces acting on the object while moving, and to produce a movie of an object undergoing projectile motion. Materials for this experiment include an iOS 9.0 or later device such as an iPhone, iPod Touch, or iPad, a meter stick or measuring tape, and in our case we used a 200 centimeter or 2 meter stick, vernier projectile launcher, a 25 millimeter ball, safety glasses, and to download the Vernier Video Physics app, which unfortunately is only available on the Apple App Store currently. It is not available on an Android device. There is a small cost of $4.99 for personal download, and it's totally worth it. Vernier Graphical Analysis 4 app is also required for this experiment. It is available on Android and Apple devices, and it is free. Place the projectile launcher on a flat surface, such as the floor. Place the meter stick or measuring tape next to the launcher along the path the projectile will be launched. Adjust the angle of the projectile launcher to 45 degrees. Place the ball inside the launcher. Do not look down the barrel of the launcher. Set the camera or phone to record on a steady surface. Launch the ball by pulling back on the lever of the launcher. In our case, a string is attached to the one in the lab. Repeat this as necessary in order to obtain a clear video. Save the video so that it may be accessed by the apps that will be used for data collection during this lab. Open the Video Physics app on your iOS device. Click the plus sign at the top left of the screen and select Choose Existing. Select the video you made from your library. It will be imported into the Video Physics app with the default name Experiment. Select Experiment. The video will open and you will see a play bar across the bottom of the screen, along with two menu options in the center of the screen titled Points and Origin and Scale. First, select Origin and Scale. You're able to drag the origin and the XY axis across the screen. Place the origin on the white circle on the projectile launcher so that the x-axis is parallel to the measuring stick and the y-axis is perpendicular to the x-axis. In doing so, the origin will not be on ground level. You may choose to place your origin on ground level, however, this will result in the projectile's initial position being greater than 0 in the y direction. Adjust the scale of your measurements by placing the scale marker in the appropriate points of your measuring stick. The app uses a default measurement of 1 meter, but this can be changed if you choose. It's not necessary to include the entire measuring stick in the scale. Select Points at the center of the screen. You will use this feature to create a frame-by-frame measurement of the projectile. To do so, adjust the video so that the projectile first appears to have launched. You may need to use the frame-by-frame review buttons in the play bar to find this precise moment. Once the initial launch is in view, drag the target to the center of the projectile. Adjust the crosshairs so that only the projectile is within sight. Hold the target with one finger and tap anywhere else on the screen, then release the target. A small red dot will appear where the projectile was, and the video will automatically progress forward by 1 frame. Repeat this process until the projectile has been plotted on its entire journey from launcher to ground. Do not plot the projectile after it has hit the ground. If you make a mistake and need to delete any of the red plotted dots, simply double tap the dot. It will turn blue and a delete button will appear. Select delete and the dot will disappear, and this will not affect your data. After you have plotted your data, select the graph icon at the top right of the screen. The app will automatically provide you with a position graph, position time graph, and velocity time graph, which you can use for analysis. Select Done to return to the video. The graphs and data can be exported by selecting the share icon on the top right of the video screen. If you prefer to use Logger Pro on a PC or Mac, select Logger Pro Graphical GW file If you prefer to use the Graphical Analysis 4 app on a smart device, select Graphical Analysis File. Select your method of sharing the file use with one of the analysis programs. Now my group partners, John and Weston, will demonstrate how to use the data that we've collected to answer questions about velocity, acceleration, and time.
To find the initial velocity of the ball leaving the launcher, you go to our x and y velocity from our chart, and you take the square root of the x squared and the y squared data to get the final initial velocity. To find the acceleration of the ball at 0.5 seconds, according to our graph, use the equation A equals the final velocity minus the initial velocity all over time. You then find the final velocity using the same method as we did to find the initial velocity. You then plug the numbers into the equation to get A equals 2.02 minus 2.89 all over 0.5 to get the acceleration A equals negative 1.74 meters per second squared. For the question, how long does it take the ball to return to its initial height? Refer to our chart in the y column and the time column, and you find the second spot where it has 0 meters, and you refer to the time column where it's parallel to 0 meters, and it says 0.7 seconds. For the question, according to the kinematic equations and calculated velocity, what is the highest point of the ball? So use equation D equals the final velocity minus the initial velocity all squared over 2g. And since the velocity at the highest point of a projectile is 0, you would just plug in 0 minus the initial velocity, which is 2.89 squared, all over 2 times 9.8 to get 0.42 meters. For part B of that last question, my answer to my calculation that I arrived at ended up being 0.1 meters above the graph data, or the chart data, which is 0.32.
Assuming the force of air on the object is negligible, what is the acceleration in the x direction and why? So this is pretty much just a trick question trying to get, you to think about some common basic knowledge, and that is that when you assume the force of air on an object is negligible, that the acceleration in the x direction is always going to be 0. And the why is just because whenever you're assuming that there's no forces acting against that ball, that's going to make the acceleration 0. For instance, the reason that there's acceleration in the y direction is because there's always gravity pulling that ball down, but there's not necessarily anything acting in that x direction when you're assuming there's no air, or the altitude isn't high enough to affect the ball. Basically, what this is asking for is the time it takes to get back to the launch height, basically. And that took quite a few steps. Starting with the way I started, at least, was I found the V naught of the ball, which, you use the equation V equals V naught plus acceleration times time, which you just plug in all the givens that you have. I chose a point from the graph to do this, which I chose the point at 0.23 seconds. So I plugged in 2.89 for the V and 0.23 for the T, and of course negative 9.81 for the acceleration. So I plugged that in for V naught, I got 5.146, and so that's the magnitude of the velocity at the starting point. And so then I use that equation to get the V naught in the y direction, which you just do 5.146 times sine of 45 degrees, and that gives you 3.64 for your V naught in the y direction. And then to find the time, I just plug that into the distance kinematic equations, and I plug in all the numbers that because it starts at 0 and it's ending at 0, basically. You're going to plug in Vy naught, which you just got, and then the time you don't know, and then 0.5 times negative 9.81 times, again, the time is unknown, squared. And then I just plug that into the quadratic formula, which ends up getting you, notice that C is 0, so that's why the -4 AC is just crossed out, because C is 0, so you're just going to use the rest of the quadratic formula, and that ends up getting you 0.746, which according to your graph, it's pretty close. On the graph, you get about 0.7 seconds, give or take 0.01 seconds, so that's very close for the total time it takes to reach the initial point. It's basically asking you what are the XY coordinates, and we'll start with that by using the kinematic equations to get those XY coordinates, and then we'll use the chart to get them. So you already have, because this is a 45-degree angle, the launch height is, you're going to use your initial acceleration in the X direction is going to be the same as it would be for the Y, so that's going to be 3.64. Your X naught is going to be 0. Your AX, as we already discussed, we're assuming is 0. The time we just found, which is 0.74 seconds, and the Y is going to be 0 also. Start by doing X equals X naught plus V X naught times T plus 0.5 AX T squared, which of course your acceleration in the X direction is going to be 0, so you can basically cut off that last part of the equation, and your initial X is also 0, so you just have this small chunk in the middle, and so that's going to give you X equals 2.69. And then your Y, of course, is 0 because it's going back down to the original launch height. And from the chart, you're going to get, quite a significant difference. It's going to be